Okay, so welcome to the second lecture on petroleum geology. And today I will first summarize why petroleum geology matters in your daily life. First of all, we are crucially dependent on energy, and that is certainly true in the industrial world. And this may surprise, actually, most of you, that the energy we consume today, in today's industrialized world, corresponds to about 200 human powers 24 hours per day. This is a calculation made by Richard Heinbrooks and others. And what it really means is that everything that's around us, the energy we see, the light, the heating, the plastic that needs energy to be produced, and whatever else, the transportation to get to your study place, etc., that is equivalent to 200 human powers, not horsepowers, human powers. Or if you want to think in terms of medieval ages, that'll be 200 slaves working for you day and night. And in medieval ages, to have 200 slaves would have been a real luxury. So that really shows you how much we are dependent on energy. Secondly, fossil energy constitutes about 85% of our energy consumption. Now that varies a little bit by country. In fact, it varies a lot by country, particularly if you look at non-industrialized countries. But in the Western world, that is about 85%. And about a third of that is oil, a third is gas, and a third is coal, on average. And there's also nuclear power, but we don't really include that here in these considerations. 85%. And we know it is a lot. Fossil fuels have a very high caloric value per volume. And on top of that, particularly petroleum and its derivatives, gasoline, are highly mobile. They are very easy to put into a tank on a ship or on a car or on a truck and can be used, therefore. It is a very, very big advantage that fossil fuels have over other sources or other energy carriers, I should say. And with that, we mean specifically, of course, nuclear power. It is not used in transportation except in nuclear submarines. And of course, electricity, which is an energy carrier, not an energy source. But there is still a big question whether actually powerful batteries can be built to drive cars over long distances at reasonable speeds. And I believe that question, as far as airplanes is concerned, is completely negative, or the answer is negative on that question, because it is highly unlikely that airplanes will ever fly on batteries. But we also know that fossil fuels are finite. And I've shown that in the previous slides. And therefore, we really have to be the stewards of what is being made and what is being made of them, how they're being used, and in what quantities they are being used. We also know that the burning of fossil fuels has undesirable climatic consequences. We all know about CO2. We know that if this continues the way it does, that it is very likely to impact temperatures on this world, not necessarily global temperatures, but certainly temperatures at higher latitudes. And those higher latitudes, they begin somewhere around here, and the effect really becomes quite catastrophic if we believe experts in this field when we go to the polar regions. But also, energy companies are very important for the economy. I showed you slides that actually demonstrate how many people work for these companies, and that's only the ones that are in the international oil and gas companies. But there's also national oil companies, and for many countries where national oil companies play a crucial role, they're also a major employer. All right, so I hope that you understand why it all matters, why fossil hydrocarbons matter, and why we should actually therefore also understand how it came to be, how the fossil fuels actually were generated. And so that's much of what we will talk about in the next lecture, and I will switch to the next presentation, which goes about the carbon cycle, organic matter, and maturation. Now, some of these terms perhaps don't tell you very much at this point, but hopefully at the end of the lecture you will be able to understand what this is all about and why petroleum, and of course also gas and coal, actually are extremely important players in the carbon cycle. So first of all, why carbon? Carbon is just an element like many others. So why is it so important in the life cycle? And the answer is surprisingly simple. Carbon has many different ways to bond with other elements, and particularly with oxygen and hydrogen. And it can form so-called organic and inorganic compounds. Now, what is the difference between those two? Well, the organic compounds are in living matter, in the biosphere, and they are considered unstable, in fact, because they are in a reduced state, and we'll get to that. The inorganic carbon compounds, they are principally minerals, really, like calcite and dolomite, and they are stable because they are in an oxidized state. And so what that really means is that carbon is bonding with oxygen and perhaps an ion, or certainly some anion. But of course CO2, for example, is in fact can be considered an inorganic compound, because it is oxidized and it's not really as such part of living matter. Okay, so carbon is contained in most substances that are vital for the development of life. There is practically no single organism on this world that doesn't contain a substantial amount of carbon. And if we have a closer look at it, the development of life and the constituents of organisms really boils down to a few select groups of biomolecules. And they are proteins, lipids, saccharides, and so forth, that we will discuss in the following. But why are we talking about all of this when we talk about oil and gas? Well, when we look at biomass on this planet, then what we see is that there is a pyramid. It's of course the food pyramid. Simple organisms get eaten by higher evolved organisms that get eaten by even higher evolved organisms. But of course, there has to be a lot more of the simple organisms in order to feed the higher evolved organisms, and therefore there's a pyramid. And at the very bottom of this pyramid, we find organisms that are quite simple at first sight and quite complex at second closer look. And they're called phytoplankton. Phyto refers to plants, it's a Greek word, and plankton is also a Greek word. It essentially refers to them as floaters. They are floating. They're floating in the ocean, but also in lakes and sometimes in rivers. So here on the picture on the right-hand side, we see one type of phytoplankton, and they're called diatoms. And what we see in blue and green is actually the living tissue. And these are very nice organisms, as you can see. And this living tissue, shows internally these radial rods that actually come from the center part of the organisms and radiate towards the outside, the outer fringe of the organism. And that's the skeleton. And that skeleton, in this particular case, consists actually of silica. So it's not a carbon. It doesn't contain carbonate or carbon, but the living tissue contains carbon. We'll get to that. Now, these organisms are very small. They're only like a millimeter in diameter. And other phytoplankton organisms actually have a carbonate skeleton. In fact, most of them do. And then we have a second group of planktonic organisms, in other words, organisms that float in the ocean, and they are slightly higher evolved. They're like planktonic foraminifera. Now, foraminifera are unicellular animals, and they contain a shell, typically, that is very often made of carbonate, calcium carbonate, calcite, in other words, but some have also other types of shells. Like radiolaria, they have actually a silica shell. So in the zooplankton world, they're the equivalent of the diatoms in the phytoplankton world. And then we have planktonic crustaceans, and those are really very small shrimp, also sometimes referred to as krill, which is one of the favorite foods of, for example, whales. Most of the biomass, and then we're talking about 90% of the biomass on this planet, is actually zooplankton and phytoplankton. And phytoplankton is much more important than zooplankton. And here we see on this slide, we see actually a planktonic bloom. So this is phytoplankton, right? It's a planktonic bloom. On the right-hand side, we see Newfoundland. On the left-hand side, Nova Scotia. So these are the East Canadian provinces. And that's the North Atlantic that we see there. And the brighter cloud that we see floating in there, that's a planktonic bloom. Because these are plants, although very simple plants. They're in fact algae, of course. And they go through stages of bloom, particularly when there are a lot of nutrients around and when the temperatures and the CO2 levels in the sea are actually optimum for their reproduction. Now, in this slide here, I show you the carbon cycle in a very simplified sketch, which comes actually from Scientific American. And what you have to look at, really, is this big circle in the middle. The upper half goes through the atmosphere, and the lower half goes through the ocean. So, since we have been at the phytoplankton bloom in the previous slide, let's look now at the phytoplankton that we see on the right-hand side of the upper half of the carbon cycle. So that's where the phytoplankton lives, and of course, being plants, they live and metabolize or use as a metabolizing mechanism. They use photosynthesis. And so how does photosynthesis work? It'll be a very interesting exercise for you to write down the equations of what plants do in the process of photosynthesis. They actually absorb CO2 and water, and they make carbohydrates out of it. They make specifically, for example, a very simple equation that you can actually write down on a piece of paper is CO2 plus H2O, right, gives a certain amount of sugar, and sugar has actually the chemical formula of C6H12O6. And so you can write that down, and what you need for this actually to take place, the catalyzing energy that goes into it is, of course, sunlight. Okay, so here we have the three necessary ingredients for photosynthesis to take place. We need CO2, we need water, we need sunlight. So phytoplankton lives relatively close to the sea, to the surface, the water surface, whether that's in the ocean or the lakes. It has to, because if you go deeper, then there is less and less light. Just like land plants, they prefer to be in places where there's a lot of light. And if you put them into a dark room, then they won't grow very well. Excuse me. All right. Now, what is the net product of photosynthesis in the growth of phytoplankton? They absorb CO2. Now, that CO2 comes from the water. It doesn't come from the air. In land plants, it comes from the air. But in phytoplankton, it comes from the water. But of course, the water, the CO2 concentration at the surface of the ocean is in equilibrium between the CO2 concentrate with the CO2 concentration in the atmosphere. There's a regular exchange of CO2. If there is too much CO2 in the water compared to the atmosphere, then CO2 will be released, and vice versa. And so it's there will be, and in fact most of it actually will be go into dissolution in the water until essentially the level of saturation is reached for CO2. And CO2, as most of you know who drink bubbly water, mineral water, is actually more soluble in cold waters than in warm waters. And that actually explains why there is actually more phytoplankton in more northern or southern parts of this planet and less in the more tropical and subtropical latitudes. And that also explains why there are more fish, more krill, more fish, and the whole food chain actually is much richer in the higher latitudes than at the lower latitudes. Although at the lower latitudes some of the fish may look more attractive, but in fact many parts of tropical seas are essentially almost deserts, and that's really very obvious when you go, for example, to the Central Pacific. Now, what happens to the phytoplankton? Well, of course, they are born, or they are created, and of course they die, and their life cycle is very short. So there is always quite a large amount of phytoplankton dying off. And when they die off, they typically fall down into the deeper levels of the ocean or of the lakes. And there they get carried because they're very tiny and they're very easily suspended, and they get transported with oceanic currents to wherever that oceanic current goes. Eventually, that oceanic current comes to an area where there's a so-called upwelling. Now, a very famous upwelling, for example, is the Benguela current on the west coast of West Africa, West and South Africa, where very cold water comes up and where deep material from fairly deep in the Atlantic Ocean actually comes to the surface, including nutrients. And this is actually a very, very rich fishing ground for that reason. And so that comes to the surface. What happens at the surface? Well, there's not only CO2 in the water, but there's also oxygen in the water. That's why fish can breathe. But oxygen and organic matter that is actually dead are a very good combination for the process of oxidation. And so what happens is this dead organic matter that gets upwelled to the surface will actually oxidize and therefore decay. And in the process of oxidation, which is the inverse of what happens in the process of photosynthesis, the organic matter gets oxidized and CO2 gets freed to the surface. And that's what we see gets freed, and much of it will stay in the water, and some of it gets into the atmosphere. And so that's what we see on the left-hand side of the circle, that CO2 gets recirculated into the atmosphere and eventually gets consumed again by living phytoplankton to actually for photosynthesis. Okay, so this is a very simple carbon cycle. Now, why doesn't the dead organic material actually get oxidized in the deeper waters? Well, there's actually two reasons for that. First of all, oxygen concentrations at the surface of oceans and lakes is typically, again, in equilibrium with concentrations, or controlled, not necessarily in equilibrium, but controlled by oxygen concentrations in the atmosphere. And so the oxygen concentrations we find there are typically quite a bit higher than in the deeper parts of any water body. And there's a good reason for that, because in the deeper parts of the ocean, of the water bodies, some of it actually decays. And the organic material decays. And that consumes oxygen. And that cannot be renewed or replenished because there is no surface, there is no contact with the atmosphere. So very often the deeper parts of oceans, of seas and of lakes are actually very low in oxygen concentrations. But I said some of it decays, and so here's the loophole, how you can escape out of the carbon cycle. And that's shown by that little arrow on the lower right. And that little arrow is actually organic matter that gets deposited without oxidizing on the seafloor, in the sediments, on the sediments, and within the sediments on the seafloor. And that depends very much on the situation we're looking at. It could be a situation where, the circulation is very slow, so quite a bit of it, which we call a stagnant body of water, and so that quite a bit of the organic material falling to the seafloor gets actually deposited and not carried away by oceanic currents. And therefore, this organic material gets deposited with sediment, such as clay, fine-grained, typically very fine-grained material, and slowly, as this process continues, the organic matter gets buried in sediment. And as we said, typically, if this happens, there is little oxygen, so even if the sediment, the organic matter gets deposited in sediment, there is no oxygen there to oxidize it, and so it'll just preserve as organic material. And so that's shown by this arrow. Now, if we go on and bury that deeper and deeper and deeper, ultimately we will get a transformation of the organic matter into hydrocarbons. And that process we call maturation, and we will discuss that later on today. Now, you said, well, that's all very nice, but the world doesn't just consist of phytoplankton, and phytoplankton, being generated and dying off and being generated again. There's a lot more to this planet, and of course that is true. First of all, what about land plants? Well, as far as land plants is concerned, almost exactly the same holds true as for phytoplankton. Trees and land plants, other land plants, they grow, they photosynthesize, and in the process they create organic material, biomolecules, and that's mostly biomolecules such as carbohydrates and lignin, which we will see in a minute. So that's leaves and the stems and the trunks and the branches and the roots and so forth. And when they die, and in our latitudes, the trees lose their leaves every time in fall, or many of them, the deciduous trees lose their leaves in every fall, and all the leaves fall to the ground, and most of them will oxidize. Some of them will anaerobically rot, and so they create methane. These are special bacteria that don't really oxidize it. But let's just look at the oxidation process. And so these leaves, they get oxidized, this organic material get oxidized. The CO2 that has been metabolized into the trees, into the leaves, gets freed again, and therefore becomes available for the trees in the next spring to actually be used again for their photosynthetic processes. And that is actually that cycle, that part of the cycle, is a relatively small cycle, you might be surprised, compared to the phytoplankton cycle. In fact, the organic land mass is much, much smaller than the oceanic biomass. But it is important, of course, because this is all around us, we can observe it, and we can appreciate also how that every year in our latitudes gets actually renewed. In tropical latitudes, that is not the case. Most trees actually keep their leaves, and so they keep photosynthesizing throughout the year. Now, what I explained so far is the organic carbon cycle, but I told you that there's also inorganic carbon. What about that? So inorganic carbon cannot get oxidized. It is oxidized, doesn't have to get oxidized. So these little critters, they have carbonate skeletons, typically calcite, sometimes another compound called aragonite. And when they die, typically, and particularly when the organic material gets oxidized, the inorganic material does not get oxidized and it falls to the seafloor. And what does it form? It forms a layer of calcium carbonate, and how do we call that? We call that eventually a limestone or a chalk. There are two different types of calcium carbonate rocks, right? And those calcium carbonate layers or limestones, typically they get deposited. I'll show you a picture in a minute. But there's also a cycle there. It doesn't stay there forever. So in other words, these organisms, they don't create calcium carbonate and then it disappears forever. Because some of these layers, limestone layers, at places where there is convergence of tectonic plates, they get subducted very deep down into the crust and then the mantle. They get heated up, and then the calcium carbonate, CaCO3, gets broken down under the influence of heat, gets broken down into CaO, which is called lime in English, and CO2, which is of course our old friend. And that is a gas, and that gas can build up tremendous pressure, and under the right circumstances, there will be an eruption to the surface in the form of a volcano in which all the CO2 that gets created in this process of thermal transformation of limestone into other components, and the CO2 will be emitted to the surface during a volcanic eruption, and that's shown here on the right-hand side with these vertical arrows, number 3, right? During large cataclysmic volcanic eruptions, an enormous amount of CO2 can be emitted. Some of these, like the very biggest volcanic eruptions that we know of, the Toba volcano and so forth, Pinatubo, quantities of CO2 had been emitted that equal or surpass the total CO2 emission that we produce with our activities, burning fuels, burning wood, and so forth, in a year. Now, where does mankind come into this carbon cycle? Because all of this here, of course, has been ongoing for a long, long time. Right? These are all natural processes that have been going on for a long, long time. And, of course, also before mankind was on this planet. But if you look at number 4 on the right-hand side, and you look to the right of it, we actually see an offshore installation. And that offshore installation, it's a platform that drills for oil, and you see these little snaky lines going down into some earth layers below. Of course, these are wells that are drilled to drill for oil, to produce oil or gas, bring that to the surface, where Mother Nature actually had the idea of keeping this underground. Well, we take it to the surface. And what do? Of course, these have a very high caloric content because it's a reduced form of organic material, and therefore it reacts very well with oxygen, which we use to our advantage to drive engines and to heat our houses. And that's shown as the arrow number 4. That's the CO2 emission that we release into the atmosphere, and that, of course, is responsible for some of the increases in CO2 concentration that we can monitor in the last 1 or 2 centuries. So what we did is we actually created a subloop, or actually we created a leak. We punctured a leak into the carbon cycle, and we're taking the fossil hydrocarbons that had been stored underground, we release it to the surface in a manner that is much more rapid than Mother Nature would do that, because also hydrocarbon-rich rocks eventually will come to the surface, but in a much, much slower process than we do that. And so we accelerate that. We actually puncture a hole in this carbon cycle and release carbon dioxide into the atmosphere. Now you might say, right, so this CO2 is good, so more plants can live. Well, the plants cannot absorb all that additional CO2 as fast as that. And what I haven't discussed so far is the red arrow coming in from the left on this picture. And this red arrow is actually an idea that some scientists had in order to accelerate actually the absorption of CO2 by phytoplankton. You need to fertilize the ocean. You see, phytoplankton does not just use CO2 and H2O. They also need other nutrients, and among others, they need iron. And so if you, for example, and that was the idea of these people, were to fertilize the ocean with iron or iron materials, iron-containing substances, then you would actually accelerate the growth of phytoplankton. Therefore, that additional CO2 that we release into the atmosphere could potentially be absorbed, at least partially, by this phytoplankton, additional phytoplankton growth, and eventually then would also be transported away, once that additional phytoplankton dies, into the deeper ocean. The only fly in the ointment of this is actually that, of course, that phytoplankton does not disappear. It'll eventually come to the surface again. And that process, arrow number 2 that we see here, from dying to upwelling, typically takes about 20 to 30 years. So if this, idea actually gets implemented, then all we really do is store temporarily more phytoplankton in the deeper oceans, but eventually it will come to the surface, and the decay rate of phytoplankton will be so much higher. So you can safely say from that, thinking in terms of cycles, that this would be a temporary solution to reduce perhaps CO2, but it would not be a long-term solution because it is not a steady state as the carbon cycle, as the rest of the carbon cycle is. Okay? So we spent enough time on this particular slide. I hope you understood it, and we'll move on to the next one. This is in fact the mass balance of carbon here. And for those of you interested in this, you can study the numbers, right? And they're actually in millions of tons of carbon. And what you see is that the amounts you find here in the ocean far surpass those in the atmosphere, and even more surpass the ones living on land. And that is really what I'm talking about. Now, the biggest number you see is in the deep ocean, so that's all the dead phytoplankton that gets recirculated there through a very, very slow process, but eventually comes to the surface. Some of it gets buried, right? So you see the number there, 38 million tons. And below that, you see in sediments, you see 20 million. And that is organic material that actually got buried. So that's taken out of the carbon cycle. Okay, but so much for this slide. If you feel free to study it in more detail. And I told you before that the inorganic carbon gets extracted in the form of carbonate-rich layers that eventually get transformed into limestones. And when you go around mountain chains such as the Alps or the Dinarids, the Zagros Mountains in Iran, and so forth, then you see a lot of limestone, a lot and a lot and a lot of limestone. And all of that, or at least most of that, is actually remainders of shells and associated products that had been deposited on the ocean floors and sometimes on lake floors, and that had been preserved as limestones. So Mother Nature has two ways of extracting carbon from the carbon cycle, and the one is through deposition of organic material, which is what this course is all about, and the other one is about inorganic carbon, and that is more a subject of sedimentology and geology in general. We will not spend any more time on the inorganic cycle, because that is really not the major topic of this course. All right, now let's go on to petroleum. And we said that quite a few, that we believe petroleum is really related to the organic carbon cycle, and therefore that it is biogenic in origin. However, there is on this planet, there is actually a whole group of scientists who believe that petroleum and hydrocarbons in general are non-organic. And these are mostly found in Russia, because in Russia, what they find is very often they find relatively thin layers of sedimentary rocks that contain oil and gas, and they're overlying what we call igneous and metamorphic rocks. And igneous and metamorphic rocks, typically, in our viewpoint, they're of volcanic origin, of metamorphic origin, deep intrusions and so forth. They have nothing to do with living organisms. So how do Russians explain the occurrence of petroleum on top of a rock that certainly has nothing to do with life? And that's why many Russians, including some geochemists, they believe that there has to be a source deep down in the mantle, perhaps, or in the earth crusts, where water, graphite, iron, and sulfur, and so forth, are actually act to form, through a very complicated process of cooking, to form hydrocarbons. And Porfiriev, a relatively well-known Russian geochemist, even postulated that all known oil fields were formed in this way in the relatively recent past, which we call the Neogene. Okay, now, this may all be very interesting, but we will see later on in the course that there is just overwhelming evidence that most, if not all, hydrocarbons that we find, and we will find, is actually organic. But carbon is common in many igneous rocks, and we all know that the atmosphere in the early days of the Earth, and then we're going back a lot, 4.5 billion years to 4 billion years, it actually contained a water vapor, it contained ammonia, it contained hydrogen, it contained other hydrocarbons. And it's a very famous experiment made in Harvard by a graduate student, where he actually put this mixture of gases and fluids in a container, and then he sent shocks of electric currents, lightning bolts, so to speak, through this mixture. And what he found was actually that very complex organic molecules originated that way. They formed. And so it could well be that in the early days of the Earth's atmosphere, very complex organic molecules had been actually generated in that way. But we believe that the large volumes of hydrocarbons, fossil hydrocarbons, cannot be explained this way. So what I show you here on this slide is the evolution of the atmosphere through time. And time goes actually down from old at the top to younger on a logarithmic scale. And what we see on the horizontal abscissa, we see the partial pressure of the gas in atmosphere. So it goes from 0 to 1. And what you see in the very beginning, at 4.5 billion years ago, we see that essentially the atmosphere was consisting entirely of hydrogen. And slowly, other components evolved, such as nitrogen and CO2. Well, where did these come from? Well, that's all through volcanic activity on this planet. You know, it didn't take very long for the Earth to form and to become a dynamic planet, such as we have it today. And therefore we also had these movements of plates and so forth, and we had volcanism, and we had CO2 that came to the surface. And this CO2 that came to the surface, and as you can see, that's the black stripe going down. It's actually quite thick in the beginning, with nitrogen evolving relatively rapidly, but relatively rapidly means over 2.5 billion years to the present-day partial pressures that we have. So that's actually a very long time. It just looks very short on this graph. And the CO2 in the air was actually, the atmosphere was actually quite abundant, and the early organisms on this planet, they actually used that early CO2 to metabolize. You know, just the abundance of CO2 in the atmosphere was reason, and of course in the oceans, because, as I said, there is an exchange of CO2 in the atmosphere with CO2 in any water body. Those plants, actually, they used that CO2 to metabolize through the process of photosynthesis. There was no oxygen at that point. Perhaps, had there been oxygen around, these early plants would have embarked on a completely different metabolism. We don't know. So if you want, you can almost view photosynthesis as an ancient way of building complex organic molecules. As these plants evolved, and they're very simple unicellular organisms, algae, and we see here widespread stromatolites, those are layered algae in shallow water. And what did they do? Because they used photosynthesis for a living, they actually produced oxygen, and slowly but surely the oxygen concentration in the atmosphere started increasing, and that's the dashed bit on the left-hand side of the graph. Slowly evolved from about 2 billion years ago to 1 billion years ago, and we see there the origin of eukaryotic cells. So those are the cells that have a nucleus. The higher types of cells, previously the organisms didn't have that. And so all higher plants and all land and sea animals, they actually have eukaryotic cells. And slowly but surely more complex organisms were developing, and those are multicellular organisms. A very diverse fauna and flora developed. There was nothing on land at this point, and in fact, up to about 450 million years ago, which is in the Devonian, a time period we call the Devonian, there was nothing on the land, only sediments, rocks, and slowly land plants evolved. And when land plants, so they slowly evolved from shallow seas, from the intertidal area, and finally they learned how to actually live on land. And so before that, the Earth was a very barren planet, a very boring planet. For the first 4 billion years, there was no life on land. And then land plants started invading the continents, and of course then, as of a sudden, there was food for the animals, for the sea animals, and so they realized that, and slowly they started evolving, some of them anyway, started evolving into land animals. Some of them didn't quite make a decision whether they want to stay land or sea animals, and those we know as amphibians and others. And of course there's a lot of lower creatures that have a little bit of both. And eventually we had reptiles, and we had much higher animals such as the mammals. And so, and that we see, starting from about 400 million years ago, evolving through geologic time. You also see that the oxygen levels stayed about, at a partial pressure of 23% or 0.23 of an atmosphere, with nitrogen being well over 70%, and that CO2 being that thin sliver that we see going down in black. So that's the development of the atmosphere through time. Again, to come back to the origin of petroleum. Well, here you see a meteorite, and it is in Namibia. It's the biggest preserved on Earth. It's very heavy. It has been actually analyzed, and you see small pieces that have been sawed off on the right lower side to be analyzed, and they found up to about 6% organic matter. And those include paraffins, aromatics, and even heavy NSO compounds, which we will discuss all later on, right? But what we see when you analyze this is that the composition, the isotope composition of these organic compounds we find in meteorites is very different from terrestrial compounds. So they probably were formed through irradiation of light elements in a primeval dust cloud, just like the experiments in Harvard that I talked about. And therefore we will assume in the following that most of the petroleum that we find on this planet is of biogenic and of terrestrial origin. In other words, that it comes from the planet Earth. All right, so let's take a short break here, and then we'll continue with the second half. Okay, so we said there's different biomolecules in living organisms, and what you see on this slide here are the most common, the four most common biomolecule groups. And we start with the lipids. They are mostly fats, oils and waxes, and in fact they have the greatest potential to be hydrocarbon sources. They are combinations of fatty acids. They have a relatively simple general formula, as you can see here, CnH2NO2. For example, glycerol would be one. If you're looking at the formula here, then you will see that it actually is complies with the formula we've seen there. Or glyceride, which is shown as a much longer compound, C17H35COOCH3. And if you group them, then you will see that it's basically N in this particular case is actually 19. Okay, so lipids, of course, all of us can relate to that, you know, fats, and some of us can relate to it a little more than others. And that's not the case with proteins. In Dutch, those are eiwit, giant molecules that make up the solid constituents of animal tissues and plant cells. And these are very rich in carbon, but also contain substantial amount of nitrogen, sulfur, and oxygen. As you see, always the same elements come back, right? Carbon, oxygen, hydrogen, nitrogen, sulfur. Yeah? So proteins, they are the most essential molecules for life, and certainly for higher life, as we are. Then we have the carbohydrates, and they are based on sugars with a very simple formula, CnH2ON. And of course, if N is 6, then we have the very simple monosaccharide sugar. And there are polymers as well, and those would be like typical like cellulose, starch, chitin, and so forth. These are very common in plant tissue, and of course, for example, if you eat a potato, then basically what you eat is starch, carbohydrates. And that, of course, is being burnt. So many plants actually are rich in carbohydrates, and that's why we eat plants for food, for energy. And lignin is then the last of these biomolecule groups. It's a polymer consisting of numerous aromatic rings. We will see later on what an aromatic ring is. It is a major constituent in land plants and converts to coal through desoxygenation. So this is basically the source material for coal, whereas lipids are the most important source material for hydrocarbons, such as oil and gas. So let's have a look at the composition of different biomolecules in organisms, and what we have here in the vertical are the different groups, the four groups, lipids, proteins, carbohydrates, and lignin. And then we have spruce wood here, a plant, a land plant, and oak leaves, and you see that they're very rich in carbohydrates and in lignin, and to a much lesser degree in protein and lipids, those being around 5 to 10% of the total. Phytoplankton, you see that lipids are much more abundant, proteins as well. Those together are about 1/3 of the total, and some phytoplankton actually, that is being considered now as a biofuel, actually has up to 50% lipids. Carbohydrates is also very rich, as is typical for plants in general, 66%, but no lignin in these floating algae. Then zooplankton, so that's little shrimp and so forth, and foraminifera. And what you see here is the fundamental difference to the plants, is that proteins become the most important group of biomolecules. They're 60%, lipids 18%, and carbohydrates 22%, and there is no lignin here as well. And with invertebrates, for example, worms or snails, then we see that these are quite similar to zooplankton, and that actually includes us to a great degree. So proteins there are by far the most important biomolecule group. And down here we see also that phytoplankton typically is 10 times more abundant than zooplankton, and 100 to 1,000 times more abundant than fish. And so that gives you, the food chain, that gives you an idea of the relative importance of these organisms. Now, if you look at the elemental composition of the biomolecules, then we see these 5 elements that I mentioned before, C, H, O, S, and N. And you see that the lipids are very rich in carbon, and the rest being subdivided equally into hydrogen and oxygen, whereas the proteins, they are much richer in oxygen by comparison, and nitrogen, because they have all these amino acids that are, part of the proteins. And amino stands for nitrogen, in fact. And they're much lower in carbon than lipids. And if you go to carbohydrates, that's even more the case, and these are extremely rich in oxygen. And that's actually by far the most important, or not by far, but it is the most important element. And finally, lignin, so wood-like substances, fiber type substances, and we see that they basically consist of carbon and oxygen, with the remainder being very low. Now, on the lowest line, you see the chemical composition of petroleum, that is typically between 83 and 87% carbon and 10 to 14% hydrogen. There's very little oxygen, sulfur, and nitrogen. These elements have all been essentially worked away in a process we call maturation. And so you see, when you look at this, the relative compositions, and now you have to just look at carbon and at hydrogen, and at the relative proportions of petroleum and lipids are the closest. And that's why lipids are really considered one of the major sources of hydrocarbons. Okay. Now, we briefly talked about where organic matter actually develops. We know that most of it is in the form of phytoplankton and of zooplankton. And of course, zooplankton to some degree actually depends on phytoplankton. And so what we really need is light, by far the most important factor. We need nutrients, and perhaps we need a little cold water, because we know that in cold water CO2 is more soluble, so that would be very welcome to phytoplankton. And what we see here on this slide is the oxygen concentration. In a schematic cross-section, you see the deeper levels on the left side of the graph. That's the deep ocean, and then we go up the continental rise, the shelf break, and finally on the shelf, right? And the open ocean waters, they are at the surface, certainly. They're fairly rich in oxygen due to circulation, waves, and exchange with the atmosphere. And as you go towards the shallower parts, the shelf, then what we have is this upwelling. And here, nutrient-rich water leads to high organic productivity. So that's pretty much all they need, all phytoplankton needs. Light, water, and nutrients. And then they start blooming. And so what that also means is if there is, so that's the organic matter engine. If you have these conditions, and you see like a typical shelf width here, 150 kilometers, right? These are enormous areas where this can happen, right? But at the same time, we also know that if you have a lot of organic growth, you also may have a lot of organic material on the seafloor. And if there's a lack of circulation, then that doesn't get circulated and there is no oxygen there. The rotting process will consume all the oxygen there is, and therefore if you have this particular situation where nutrients get actually ferried in from oceanic circulations, and you have a shallow sea that has a very low degree of circulation, but otherwise all the components are in place for organic growth, then you will also have a very rich organic zone on the seafloor, because there, with this growth there will be a lot of dead material falling to the seafloor that will consume all the oxygen, and that is actually where most of the organic rich rocks that we consider source rocks are generated. So now we take a very short break and we look at some study questions, just to make sure that you relate to this. Everything I said so far has to do with your daily life, basically. For example, you can ask a question: what organic biomolecules did your breakfast contain today? Did you drink milk? What contains milk? Did you eat eggs? What kind of biomolecules are in eggs? Bread? Did you have an orange juice? What's in an orange juice? And so forth. Or a cheese. Did you have French fries? Did you have a hamburger? So just think about it, because actually all of these 4 biomolecule groups that I showed you are actually part of our daily food. Then what is the principal difference between your metabolism and that of plants? What is the open ocean? Why is the open ocean less favorable for phytoplankton growth than shelf areas? What happens to the carbon cycle if all the ice caps melt? And write down the basic chemical formulas for the formation of sugar through photosynthesis, the burning of a simple lipid, the transformation of carbonates at high temperatures. All right? And we'll address in the next lecture, we'll address these questions. We'll move on here. And now we talk about the preservation of organic matter. We know how it is being generated, how most of it is being generated. We know that the biomolecules are reduced forms of carbon and hydrogen. If we want to preserve it, we need conditions where oxygen is absent. And we call those conditions anoxic conditions. If we talk about a stratified basin, that could be a lake or could be part of an ocean or a sea, where circulation, vertical circulation, is very low or absent, there will not be any transport of oxygen to the greater depths. And that provides very excellent conditions for the preservation of organic matter. And a very good example of this is the Black Sea. It is salinity stratified. It's relatively fresh water at the top, and below that, below about 30 meters, it is actually, it is essentially stagnant. It doesn't move. It's saline. It's a sea, fully saline, but it doesn't move. And in fact, the water is not for nothing called, or this body of water is not for nothing called the Black Sea, because actually there's a lot of organic matter there that doesn't decay, and that gives it the black color, the dark color. It is completely anoxic. In other words, if you are a fish swimming there, and then at the end of your life, you die, and you fall to the seafloor. First of all, you fall through these 30 meters of relatively oxygen-rich fresh water, brackish water, and then you reach these 30 meters, and that's not enough time for you to decay. And after that, you're in an environment that is completely devoid of oxygen. And you'll fall to the seafloor completely preserved, or almost completely preserved. There may be actually critters actually eating you. But you're falling to the seafloor very well preserved. And of course that happens to phytoplankton as well. That happens to a lot of, so there's a lot of organic matter in the Black Sea that gets deposited on the seafloor. But also the lakes around here, in the Netherlands, in many parts of the world, are actually anoxic. And that simply has to do with the nutrients that come from agricultural activities into these lakes that actually leads to excessive growth of algae every summer. And they die subsequently, and as they die, they get oxidized, and they consume all the oxygen in the deeper parts of these sea bodies. And so most of them are actually, or many of them anyway, are anoxic, particularly if they really don't have a lot of circulation. But that's man-made. Now, we know that oxygen is not good for preservation, so essentially what happens is organic matter will get oxidized into CO2 and H2O, and that's the normal carbon cycle that we talked about. And so what we're talking about now is that little side arrow that goes down into the sediments. So let's look at how much that actually is. So the total carbon content in the Earth's crust is a whopping 9 times 10 to the power 19 kilograms. That's total carbon. Most of it we saw. Most of it, remember where it is? It is in the limestones, in the deep sea sediments, and so forth. The biosphere and hydrosphere contain less than 10 to the minus 5 of this. That's 0.001%. And over 80% of this, of the total volume, is in carbonates. So the organic carbon amounts to 1.2 times 10 to the power 19 kilograms, and it is distributed approximately as follows. So we see these numbers. Dispersed in sedimentary rocks, 97%. Petroleum in non-reservoir rocks, 2%. Coal and peat, 0.13%. Petroleum in reservoirs, 0.01%. So what does this tell us? What's dispersed in sedimentary rocks mean, really? Well, if you look at the rocks, such as the ones that are used to have, like, make door sills and stuff, you know, what's called in Dutch the lijsteen, it's a gray rock that you see, you know, and in the houses being used to actually prevent humidity from rotting the window, the door frames. And so if you look at them, the door steps, for example, they're grey rocks, but if you look at a fresh cut, it is actually black or very dark grey. And that dark color comes from organic matter that's in there. It only has like 1 or 2 or 3%, not very much. It's a rock that actually comes, a limestone that comes from Belgium, from the Ardennes. Right? It has organic material in it. Some of it is actually quite rich. When you polish it, it becomes very nice and dark, right? And is actually being used, these very famous Vermeer paintings, where you see the kitchen floors being black and white tiles. Well, the black ones are actually these rocks. And the white ones is marble that comes from Italy. Very, very clean limestone. That's recrystallized, and that's called marble, right? And so there's the difference between an organic-rich limestone and a very clean limestone right there, and that gives the color difference. And that's where 97% of the organic material is. Petroleum in non-reservoir rocks, what's that? Well, petroleum is actually all over the place, but it is in very minute quantities, which we cannot produce. And we'll get to that because it has to do with migration and the efficiency of the migration process. Only 0.01% actually winds up in a reservoir. And what does a reservoir mean? It means a place where we can actually drill a well into and the oil can actually flow through the reservoir rock to the well and we can produce it. So this really illustrates the very low efficiency of the preservation process of organic matter. Now, what we look at when we look for oil and for gas, we look for a rock that contains a significant amount of organic carbon. And we call that a source rock. And that, the primary parameter we look at is total organic carbon. How much carbon is there in that rock? So this is not the reservoir. This is the source where the hydrocarbon gets formed through this process of maturation. So what we see here is a very simple table. If the total organic carbon content in a rock is between 0 and 0.5%, then its quality as a source rock is very poor. Up to 1%, it is fair. Up to 2%, it is good. Up to 4%, it is very good. And above 4%, it is excellent. The Kimmeridge clay, for example, in the North Sea, can have up to 8% TOC. It's an excellent source rock. But it is nothing compared to the Silurian source rock in North Africa, in Libya and Algeria, which is pitch black. And it has up to 30% total organic carbon. But most of the time it's between 10 and 20%. Very, very high. And these are exceptional, of course. But when we look at such a source rock, and this is an example here, which comes from Iraq, from a well called Saddam 8, which I don't really make up. And then what we see here is this is a slide, a thin section that's only a few millimeters wide. And so the grains we see in various colors and brightnesses, these are little clay and calcite particles that are very finely distributed and laminated, and then there is sort of a break, which is a small fault actually, and on the right-hand side is very dark, and you see more of these brighter particles in there, all very fine. Typically, these are actually a few thousandth of a millimeter wide, these particles. Right? So that's a clay stone. And in the clay stone, or a calcareous clay stone, I probably should say, there is carbonate, there is organic material. In this case, this is also a very rich organic rock. It contains typically about 5 to 10% organic matter. It is one of the major source rocks in the Middle East, in Iraq, and we'll have another look at it here. We see actually here in pink, in the upper half, we see this very strange arrangement of particles. In fact, this is a very small animal whose bones are preserved. It's only a few millimeters wide, probably a small critter like a small shrimp, but we don't really know what it is, or at least I don't know what it is. And the rest is all very fine-grained material again. We see small quartz grains, small carbonate grains, and the dark ones are clays, and in the dark parts there's also organic matter. So it's the same source rock as the previous slide, just by way of illustrating how these things look like. The relationship between total organic carbon and hydrocarbons is plotted here on this graph. On the horizontal axis, the organic carbon is shown, and on the vertical, the hydrocarbons in that same rock. So what we do is we take a sample, we analyze it, both for its total organic carbon and for how much hydrocarbon it contains. Again, this is not a reservoir rock, it's a source rock. So these are shales, coals, some sandstones, and so forth. And what we see is a general trend from low to high on both axes. And the only exception actually being some triangles above that shaded area that actually represent sandstone samples that are much richer in hydrocarbon than the average trend, because those are actually reservoir rocks. But the rest are source rocks. except for the coals, sorry. They're at the very right upper end, just pure coals. But that's more for reference. What we see, most of the hollow triangles and circles and crosses and the field circles, they show a very nice correlation of organic carbon with hydrocarbon. In other words, the more organic carbon I have, the more hydrocarbon we find. And so this is the most important argument for the biogenic origin of fossil hydrocarbons. This slide here. It is a much stronger argument than anything that we find from the inorganic proponents of the abiogenic or inorganic origin of hydrocarbons. Now, what kind of total organic carbon, what form does it take? And we can subdivide organic carbon into two types. Of course, originally it's been lipids and proteins and lignins and so forth. But at very shallow depths, in fact, they get transformed into something else. And one of them, organic types that we find in the subsurface, is bitumen. And that is the fraction of organic material that is soluble in organic solvents, such as chloroform, turpentine perhaps. And the other one is kerogen. And keros is Greek, means wax. And that's an insoluble in organic solvents. It's insoluble, it's non-extractable, but it actually forms in the transformation from organic matter. It's an intermediate product. It forms as there is a heating going on, as layers get buried deeper and deeper and deeper. They're reaching higher and higher temperatures, and that's where kerogen gets formed. Kerogen is the principal source of hydrocarbon generation. It's a very complex mixture of high-weight organic molecules. And what you see here is a formula, C12, H12O, and 0.16, and then an X. But that's just an approximate formula, as you can see. But what you see here, compared to the previous compositions of the lipids, and particularly of the carbohydrates, which are very rich in oxygen, the oxygen is almost gone here, right? There's very little left. And so what happened here was this kerogen is actually an organic material that's much richer in carbon and hydrogen than the original organic substances are. And we see that here as well. We see actually on this triangular graph, which you really should watch out because it's not the full triangle. It only goes down to 30% H and 30% O on the left and right hand side, you know, respectively. In other words, the lower horizontal line is actually 70% carbon. That's what it is. And so what we see here is kerogen is extremely rich in carbon. And this is, in fact, these are weight percent here. And what's the band that says oil shales is very, very close to the band that says coal. And coal, of course, is almost pure carbon. It has a little bit of water, and that accounts for the H and the O that we see. It's much more shifted towards the O side because O is heavier than hydrogen. And we see the oil shales somewhere in between, but going very strongly towards carbon. And these are very typical shales that are actually source rocks. And the one with the whatever it is, a rhomboid, is the Kimmeridge clay from England. So that's the North Sea, major North Sea source rock that we see there. All right. So what happens really to in the formation of hydrocarbons? So we know that, first of all, the organic molecules, biomolecules, they get exposed to higher and higher temperatures. And what that means is that the CO2 and H2O will actually be expulsed. And sometimes, actually, bacteria help in that process. And they actually extract also sulfur. And many, many formation waters, for that reason, actually contain very low sulfate. Kerogen gets formed, which is very low in oxygen. It's rich in carbon and hydrogen. And CO2 and H2O have actually been, for a great degree, have been expulsed. So this is a process called deoxygenation and dehydrogenization, which we'll look at in a minute. Methane is formed and hydrocarbons are formed. And so as maturation, this transformation of organic matter to hydrocarbon takes place, the carbon content increases. And so what we see here is in the form of, in the example of coal, we see the hydrogen to carbon ratio. And we see on top, we see wood has a hydrocarbon ratio 1.5. This is in weight percent. Peat 1.3, and these are successive stages of coal formation. Lignite 1.0, bituminous coal 0.8, and anthracite has basically no hydrogen left, is pure carbon. So the dehydrogenation process and the carbonization process are complete when the coal reaches the stage of anthracite. Now likewise, in petroleum formation, we actually have a deoxygenization process and a carbonization process. And so if we look at the organisms, typical organisms or biomolecules, the oxygen over carbon ratio is 0.35 to 0.6, as we've seen before, earlier on. If we go to kerogen, that is down to 0.1 to 0.2, again weight percent. So oxygen gets removed. And if we go to petroleum, it essentially is devoid of oxygen. It's the equivalent of coal in the petroleum world. So what really makes a source rock be a good source rock? First of all, we've noticed is the total organic carbon. And secondly, we also need to look at the quality, the level of the H/C ratio. So the higher this ratio in fact is, the better it is actually as a source rock before thermal maturation. And as the thermal maturation proceeds, hydrocarbons are formed. The kerogen will continuously deteriorate as a source for hydrocarbon formation. In other words, what's left behind becomes more and more and more difficult to transform into petroleum or into hydrocarbons in general. What we see here is a diagram called Van Crevelen diagram. It's a researcher who actually worked for Shell. And what we see here is the transformation of organic materials, different types, in fact, of kerogens. And there are 3 pathways of kerogen. And we look at them one by one. But the graph is actually shown on in a reference frame of O/C ratio on the horizontal versus H/C ratio on the vertical. And what you see is at the very top, we see resinite. It's a type of kerogen that gets formed from algae. And you see the vertically dashed bit at the very beginning. This is called kerogen type 1, in fact. That's why there is a Roman numeral 1 there. Initially, only CO2 and H2O get expulsed, and then we're reaching along the arrow, we're reaching a white zone, and it says oil. That white zone says oil. And so at that stage, oil gets formed. And the H/C ratio continually decreases, but in this case, there is very little oxygen in the system, so it doesn't really change very much. It stays at about 0.05 O/C ratio and just moves vertically down. So hydrocarbon is formed in the form of petroleum. We move further down and then we come to this dark area, and that's where gas is being formed. And what's shown really is how much that kerogen ratio, the remaining, what's left over, how that ratio behaves. So it actually becomes more and more like coal as this resinite expulses more and more hydrocarbon. What's left behind is richer and richer in carbon and starts looking more and more like coal. Now we move to the right, we go to kerogen type 2, and we see that these are mainly phyto and zooplankton, so that's typically what we find most of the time. And again, we see how along the arrow, we go from initial CO2 H2O production to the expulsion of oil and finally to gas. And of course, in this case, because there is more oxygen in such systems, there's also a decrease in the oxygen over carbon ratio. And eventually it joins up with a resinite kerogen to form very carbon-rich compounds. And on the very right-hand side, we see humic kerogen. Now that's land plants. And so we know what the origin is of that, and that's mostly lignins. And we see, so there's a lot of oxygen in there, so it comes mostly from the right-hand side. The H/C ratio also decreases a little bit, but it's already low to start with. And then it slowly moves through the expulsion of CO2 and H2O to where oil is getting expulsed, and finally to gas. How do we know all of this? How do you know what this happens? Well, we can, of course, drill holes, and we can take samples, and we can measure that, and we can also measure how much oil is around and what's the composition. So we can measure the kerogen composition, we can measure the oil composition. And that's how these things have been determined. But how do we know at what level this rock is? Now, you see these dashed lines, and these dashed lines are so-called maturation indicators. Because you see, if I'm working for an oil company, an exploration geologist, and my boss says, go to that and that region and check if there's a potential for oil or gas. The first thing I have to figure out, is there a source rock in that area? And the second thing I have to find out, how mature is it? Did it actually form oil or gas? If there's no source rock, I can go home immediately. If there is a source rock and it is not mature, I also go home because I know nothing has been formed, no hydrocarbons have been formed. But if it's mature, and then I need to know how mature it is. Did it form oil or did it form gas? And so I need indicators. And what's called VR at the very top of the graph is called vitrinite reflectance. And there's also in the middle of the graph, it's called TI, and that's also another maturation indicator. And you see that these maturation indicators, in fact, they show at what level oil is formed and at what level gas is formed. So how do I measure these indicators? Well, these indicators are essentially nothing else than thermal indicators. Or in fact, to be more precise, they're actually time temperature indicators. How long has a rock been at a certain temperature? And on the left-hand side in this graph, we see the well-known transformation of coal from lignite to bituminous coal to anthracite. And that has to do with temperature. And, and there are, because we don't really talk too much about coal in this particular class, but at the same time we can also look at clay minerals, how they change, because clays, as you bury them and expose them to higher temperatures, they actually change from so-called smectites to illites to chlorites. So if I look at the clays, and then I can actually predict at how deep these are buried. And you see on the very left-hand side of this graph is called LOM, level of organic metamorphism. That's the degree of organic maturation. And this is, this is a little bit subjective here, but it basically says that the lower you go, the more likely this source rock is to be mature. And so I can look at the clays. I can look, if there's any coals, I can look at the coals. So if I see bituminous coal, then I know that I'm quite high, at a high level of organic maturation. And on the very right-hand side, we see the formation of first early diagenetic methane, which is at very shallow depth, then finally oil. And oil, as we proceed, actually gets transformed, decondensate into gas. And finally, at the very late stage, actually gas gets formed, just as we follow the von Crevelen diagram. So how can I actually, how can I determine that? Well, I can look at the clays, I can look at the coals, but I can also look at other indicators that I will show you in a minute. Now, how do we know that things have to do with temperature? Well, we can simply look at these rocks, go to a certain depth, take a sample, and look at what's in there. And we're still talking source rocks, not reservoir rocks, because that's a different story. Source rocks, clay-rich rocks that have organic material, right? And we can look at what kind of material we find in there. So we know there's kerogen in there, but what else? And so we can look at it, and this graph actually shows at what temperature these rocks are, at what depths these are, and what we find in them. And in the middle are two lines, right? And in between those lines, we see what we find in there. On the very left side, at low temperatures, we find heavy oil, and the further we go to the right, we find gas, light oil, and then gas, mostly gas, and then gas only. And what are these two lines? Well, these are so-called thermal gradients, geothermal gradients. One of them is a line that is equivalent to a temperature gradient of 20 degrees per kilometer. In other words, if I drill a hole 1 kilometer deep, I have a temperature of 20 degrees plus the surface temperature. In the Netherlands, that's 10 degrees on average. So that's 30 degrees. And the other one is a very high geothermal gradient, such as we have in certain areas, 50 degrees. And so that with every kilometer, the temperature would increase by 50 degrees. And most rocks in most areas fall somewhere in between. So what we find is, with increasing depth, we find increasing temperatures. And with increasing temperatures, we find lighter and lighter oil, and finally gas. And so here we see a very simple graph that shows on the vertical temperature and on the horizontal time. And we see that this line, the solid line, that shows actually that in the time, this geologic time, that very young rocks, which are indicated by tertiary here, they need to be exposed to more higher temperatures than the older rocks shown as Cretaceous and Jurassic. They can stay at temperatures like 75 to 50 degrees, but because they are older, they are a longer time exposed to those temperatures. And that's why it's not only temperature, but only time that is important in maturation. So a young rock has to be exposed to higher temperature than an older rock, who has been exposed to a lower temperature, but for a longer period of time. So these maturation indicators, they have to tell us, is there a potential source rock, how much there is, and how it relates to oil types. And from that, we can actually determine the time of hydrocarbon generation, migration, and accumulation. And ultimately, because my boss sent me to some area where I have to figure out if enough volumes of hydrocarbons are generated, if I do the analysis properly, I can actually tell him how much there is. There is many ways of doing that, and one is actually developed by Mr. Lopatin, who is a Russian, who recognized that temperature and time are important. And he developed a so-called TTI, temperature time index, or time temperature index, TTI. It's an integral. It's an integral that looks at the time, the interval of time a rock spends at a certain temperature or at a certain depth. And so without going into details, so you understand that, if a rock doesn't go very deep, then in order to become mature, to produce hydrocarbons, it has to stay a longer time at that relatively shallow depth. What we see here is a very simple graph of geologic time on the vertical versus depth, and we see that old rocks on the left-hand side, they go down, they get buried deeper and deeper and deeper and deeper. At one point, shown by A here, these rocks actually reach the so-called oil zone. And then following that line, they would actually get deeper and deeper and deeper, and they'd stay in that zone until they reach the second semi-horizontal line, and they would actually move into the gas zone. Right? So that's the amount of time this rock actually spent in the oil zone where oil gets generated. So from that I can actually calculate the amount of hydrocarbons that would be generated. All right, now you see an older rock, which is older than Cretaceous, it's Jurassic, which actually reaches B at the same time as the Cretaceous rock reaches A, the oil zone. It actually is already for quite a long time in the gas zone, that older rock. And so that particular rock probably is very gas prone. It produced a lot of gas, whereas the Cretaceous rock produced a lot of oil. If you look at the Paleogene rocks, they've only reached a moderate depth, shown at the very right of the graph. And so they barely reached the oil window. And so any source rock, potential source rock there is not mature. So you can look at it yourself and figure out at what time actually the rock of age A will actually reach the gas window, and you can try to plot that on this particular graph. So the TTI index is actually, it's a calculation. You have to know what happened in a particular basin. But most others are actually sensitive to temperature and time in an indirect way. And the most important one is vitrinite reflectance. What you do is you actually take kerogen, little pieces of kerogen, and you look at their reflectivity under light. And that actually correlates with fixed carbon. As very little is reflected usually, so these ratios are very small, 0.5 to 1.3, typically is a value that indicates that this rock has been in the oil window. It's laborious but widely used. Then we have the thermal alteration index, which is, again, we're looking at organic matter, but this time we don't look at reflectivity, but at the color. And it is originally pale yellow, like leaves you can think of, and it goes to black, which is 5. In fact, unfortunately, this index is very simple actually, but it has a poor sensitivity within the oil window because it's always between 2.5 and 3. It's not generally used. And then we have this level of organic maturation is based on coals, as we've seen that before. And so how do these actually correlate? These thermal maturation indicators. Well, we see here just a simple table, and we see Lopatin's index on the first column. You see that it has a very wide dynamic range, and we see that anywhere between 15 and 160 it'll actually, and we don't really know what these units are because we haven't discussed them, but that's when the particular rock is actually in the oil window. And for the vitrinite reflectance, designated by R-NOPE, that's between 0.65 and 1.3, perhaps going up to 1.5 sometimes for very light oil. And then we see a thermal alteration index on the right-hand side, which actually has this very low sensitivity, as we said, because it's based on subtle color changes that are not very sensitive to the degree of maturation, certainly in the oil window. So the one thing to retain here is that the vitrinite reflectance is easily measurable. It is a good indicator for oil and for gas. If you go a little further down on the table, you see that the gas typically is generated between a vitrinite reflectance level of 2.0 and 4.8, or perhaps even 5. All right, so that's all for now. Thank you very much. We continue with the next lecture next time. Thank you.